So that took a whole hour and a half to do that.
That's an extra.
Okay. All right, so inverse function. So if we've got two functions, f and g, such that f of g of x ends up being just x for every x in the domain of g, and g of f of x ends up just being equal to x for every x in the domain of f, then the function g is the inverse function of f. It is denoted f, it looks like an exponent, but it's not. F to the minus 1, f, we read f inverse. F inverse. So f of f inverse of x equals x, and f inverse of f of x equals x. The domain of f is equal to the range of f inverse and vice versa. So show that each function is the inverse of the other. So we're going to show that this is the definition, and I did draw this up, you know, composites. Well, now we got, if we got x going into g, we've got g of x coming out, and then that's going into f, and if we get x out, they're inverses, and vice versa. We can have x going into function f, we get f of x out, f of x going into g, and if we just get x out, f and g are inverses. That's the pictures for these. It's like tying your shoe and untying it. So let's see, we're going to show that these two functions are inverses of each other. Did I show a calculator ever today? Because I don't know if it showed up on there. No, I don't even have the calculator chosen. Okay, we haven't had to use a calculator today. Okay, so we're going to show that these are inverses of each other. So this is the definition. So we're going to show that f composite g is just equal to x. So f of g of x is f of x minus 9 over 4. Then everywhere in f of x that you have an x, you're going to replace it with x minus 9 over 4. Sorry, too big. Okay, so when you do that, you get 4 divided by 4 is 1. So now you have x minus 9 plus 9, and you get x. And so you show it the other way. G composite f equals g of f of x will be g of 4x plus 9. Everywhere in function g where you have an x, you're going to replace it with 4x plus 9. So there's our function g. We're going to replace it with 4x plus 9. 9 minus 9, 0. 4 divided by 4 is just x. You get 4x divided by 4 is x. So these are functions, or they are inverses, I mean. And if it doesn't come out so nice, they're not inverses. You can try it. I didn't show an example where you get a mess that nothing cancels, and don't start trying to make things cancel when they don't. So, I mean, if I had, so, I never should. I'll just show you, what if I was checking to see if 4x plus 9 and let me just show you, say it's x plus 9 over 4. We want to see if those are inverses. Well, when you do f composite g, f of x plus 9, I just changed the problem and it's not going to work. Okay? Everywhere I have an x, I replace it with x plus 9 over 4. In this case, I made it too nice still, but it's still canceled here nicely. I get x plus 18. So they're not inverses. You can stop there and say these are not inverses. Okay, so just added another thing. All right, so if you want to be able to find the inverse of a function, here's the steps you can do, and it's not too hard. What we're going to do to find the inverse of a function, and an inverse has to be a function too. So if the inverse ends up not being a function, we say that it doesn't have an inverse. So we're going to replace f of x with y in the equation for f of x. Then we interchange x and y. Then we solve for y. And if it doesn't define y as a function of x, then f does not have an inverse. If this equation does define y as a function of x, the function has an inverse function. And then the last step is you want to replace y in step 3 with the correct notation, f inverse of x. So don't forget the notation. So we've got find the inverse of f of x equals x plus 7. So you're going to do these steps. Step 1, you're going to replace f of x with y. Now you're going to interchange x and y. And then you're going to solve for y. So let me write y on the left. Y plus 7 equals x. Subtract 7. Y equals x minus 7. Is x minus, so this is step 3. Is x minus 7 a function? Yeah, you only get one y for every x. So it's a function. So you replace step 4, you're going to replace y with f inverse of x equals x minus 7. That's your final answer. All right, we're going to do it for a little more complicated example. Step 1, replace y, f of x with y. Step 2, switch your x's and y's. And in graphs, that works too. You can switch your x and y coordinates, and we'll be doing that later. So x equals 2 over y minus 4. Now you need to solve for y. So I want to add 4 to both sides. I get x plus 4 equals 2 over y. now I can write this as a fraction and cross multiply. I can write that and cross multiply like that. Make x plus 4 as over 1. A fraction equals a fraction. And we can cross multiply. Or I could have multiplied both sides by y. Same thing. So we get y times x plus 4 equals 2 times 1 or 2. And then I want to divide by x plus 4. So y equals 2 over, that's a 2 now, doesn't it? X plus 4. Is that a function? Well, it's not y squared equals something, so it's a function. So we're going to replace it. F inverse of x equals 2 over x plus 4. But okay, so that won't be given to you for the next test. How the steps? You have to do it enough and memorize it. That's how you can find the inverse function of a function. All right, the horizontal line test for inverse function. In order for something to be an inverse, it has to be a function. So the horizontal line test says a function f has an inverse function if there is no horizontal line that intersects the graph of the function f at more than one point. So it's like the vertical line test, except this is for inverse functions. So this is a function, it's an absolute value function. You can do the vertical line test, this is a function. But can you do does it have an inverse? Well, if you do the horizontal line test, you can go through 2 points. It doesn't have an inverse. So, I have an extra example here, because you'll get these in MATLAB anyway. If you have a function 2, 1, and just 2 ordered pairs, and 6, 1, this is a function. It's a function because it has the same y values, but it doesn't have the same x's. If I draw these points over here, 2, 1, and 6, 1, because you can draw a horizontal line through them and go through both points, this does not have an inverse. Because it's not a function. You can try to find the inverse by switching the x and y. So for ordered pairs, you can try to find the inverse by switching them, switching the x and y's. So 1, 2, and 1, 6. Is this a function? No, it has the same x with 2 different y's. This is not a function. But we've showed if you have an equation how to find the inverse function, but if you have ordered pairs, how do you find the inverse? You can switch your x's and y's. But if what you get is not a function, then the original function does not have an inverse. or you could do the horizontal line test for inverses on the original function. Did I confuse you? All right, so if a function passes the horizontal line test, we say the function is one-to-one. A one-to-one function is a function in which no two different ordered pairs have the same second component. So I gave you that extra example. This was a function, but it doesn't have an inverse, and it's not one-to-one. If it has an inverse, it passes the horizontal line test. We say it's one-to-one. If we just change this to a different number, like 2 or 3 or anything else, it would have been one-to-one and had an inverse. Okay, so the graphs of f and f inverse. The graph of f inverse is a reflection of the graph f about the line y equals x. So we can use the graph of f to draw the graph of its inverse function. We're going to use the same coordinate plane. I don't know how we do that if we had to go out here, but okay. We got permission to use the same coordinate plane. So the thing is, just label these points. This is -6, 1. This point is 2, 5. And this point is 4, 6. So if we want to draw the inverse function, here's our points. We're just going to switch our x's and y's. So these are going to become, we're going to have 1 minus 6, 5, 2, and 6, 4. So 1 minus 6. That makes sense. That was that one. 5, 2. And 6, 4. You switch your x's and y's. And then it helps if you have a straight edge. And so this is your inverse function. And you can see that it is the reflection. This is the line y equals x. Let's see if I can get that in the right place. Close enough. Okay. If I dash in the line y equals x, okay, this orange line is y equals x. And this black line is reflection to get its inverse, a reflection about that line. So we can just switch the x and y coordinates, and when you have a graph like this, that's the easiest way. The straight line is the easiest way to draw the inverse, is to switch the x and y coordinates. Okay. All right, another example is if we've got find the inverse. Okay. This function actually would not have an inverse, except we're going to restrict the domain so that it will have an inverse. Okay, so we had and y equals x squared would be up here. And so if you remember the 1.6 section, if we're subtracting 3 on the outside, that shifts it down 3 to negative 3. So this is y equals x squared minus 3. And if we do the horizontal line test on x squared minus 3, it goes through 2 points. So it doesn't have an inverse. So what we said is let's just make x be greater or equal to 0. So that means that we got rid of this part. So now on our graph, we just have this part. We just have half a parabola. Does that have an inverse? Yes. So this is half a parabola. That's why it originally wouldn't have an inverse. It wouldn't pass the horizontal line test. But we made it so it would have an inverse because we said we're going to only allow x to be positive. So now we do the same stuff here. We replace f of x with y. We switch our x and y coordinates around. X equals y squared minus 3. Then we solve for y. Y squared minus 3 equals x. I want to switch these around and add 3. And then we take the square root of both sides. And usually it's a plus or minus sign when we take the square root. But because of the original restricted domain, we're only going to get the positive one, the principal square root, because we were only doing this part. And if you reflect that about the line y equals x, you're going to get something like this for the inverse. See, we restricted the domain is why we only have the positive. And so it does have an inverse because of the original restricted domain. So our step 4 is f inverse of x equals the square root of x plus 3. So this was step 1, 2, solving for y, and then last step 4. And I drew the picture to show you the inverse is in green here. This original function, it reflects about y equals x. Okay, so on the last page, any questions? Okay. Is it still all review? Oh. Maybe you didn't really need this class.
Well, I took it as a senior in high school, like pre-cal, but it wasn't the same like standards that you guys have.
Oh, okay, okay. Well,
And my ACT score wasn't high enough.
oh, that's what it was. Well, anyway, you'll have a very good background then. It gets harder as we go, but you'll have a good background for 1720. So this is going to help you. All right. So the last example. First, we're going to find an equation for f inverse of x. So we're going to do that, part A. We're going to replace f of x with y. We're going to switch our x's and y's around. Now we're going to solve for y. So 3y minus 4 equals x, add the 4, 3y equals x plus 4, and then we're going to divide by 3. You can either do that, divide the whole thing by 3, and that is a function, so f inverse of x equals x plus 4 over 3. That's the answer. You could write the answer as 1/3 x plus 4/3. Any of these forms, you know, you could distribute that divided by 3. But there's our either answer. These are both right. Okay, now we're going to graph f and f inverse in the same plane. So f has a slope of 3 over 1 and a y-intercept of 0 minus 4. So we start at the y-intercept, and then we're going to go up 3 over 1, up 3 over 1, then we can go down 3, left 1, and then we can grab our straight edge. This is the line, y equals 3x minus 4. Here we go. Or f of x equals what? 3x minus 4. Okay, so now to graph the inverse function, the easiest way is identify some points here. 0 minus 4, and it's going to be a straight line. I mean, it's going to be harder to start at 4/3 and go up 1 over 3 because it's not on a whole number. So we're just going to notice that it goes through 2, 2, and switch these around. So 0, -4, and I'll do it in green, becomes -4, 0. And 2, 2 switched around is still 2, 2. And we can do more points if you want, but 2 points. And we can go, the slope is go up 1, right 3, up 1, right 3, up 1, right 3. But anyway, I've got the rule. There, that looks pretty good. F inverse of x. Oh, and this is f of x. So you want to label your graph, and you can draw the y equals x if you want, but notice they are, you don't have to draw the y equals x. Oh, orange. Here's y equals x. So, all right, in the last part, so you see, we got graphed f of x easily using the y-intercept, slope-intercept form, and then we were able to find, and it looks like this, when this goes through 4/3, it looks like it, but it would have been hard to graph it, starting at 4/3 and going up 1 over 3. And the last one is give the domain and range of f and f inverse. So for f of x, it's a straight line. This is kind of f of x is the blue line. The domain is minus infinity to infinity. It's a slanted line. It goes out. This is going down at an angle and up at an angle. It's got all real numbers. The range is all real numbers, minus infinity to infinity. But, so this is kind of a bad example, but if these were different, the range of this will be the domain of this one, and the domain of F will be the range of F inverse. And it's pretty boring because they're the same. But they would switch, and you can see that if we'd done a harder function. You can see if we wanted to go back and do domain and range on the previous page example, that would be a little more interesting. But, and that is section 1A. Any questions? So that was what we were supposed to cover for today. You can work on MathLab, and you got 3 things to do with Shobi for next time. So